Welcome to The Explainer. Today, we're going to do something pretty cool. We're taking a classic piece of lab equipment and giving it a serious hardware upgrade. Yep, we are going to turn a super sensitive measuring tool into a totally new, robust device, and we're going to do it with just one simple component.
So here's the game plan. First, we'll get to know our starting gadget and its biggest problem. Then, we'll sketch out the blueprint for our upgrade, actually put the hardware together, and run a full diagnostic to see if it works. And finally, we'll dive into the simple physics that makes this whole thing possible.
Okay, so let's meet the star of our show, the galvanometer. Now, before we can even think about upgrading it, we really need to understand what makes it special and what its one major weakness is.
And right there, that's the heart of our challenge. Think about it. We have a job to do, measure a pretty big voltage, but the only tool we have is so delicate that the exact thing we're trying to measure would completely fry it. So how do you solve that? How do you use a sensitive instrument to measure something powerful without breaking it? That's the puzzle.
You've got to understand, a galvanometer is a true specialist. It's designed for one job and one job only, to detect the absolute faintest whispers of electric current. I mean, that sensitivity is its superpower, but it's also its kryptonite. Asking it to measure, say, 10 volts is kind of like trying to weigh a semi-truck with a scale designed for feathers. The tool just isn't made for that kind of heavy lifting.
All right, so we've got the problem locked down. Now for the really fun part, the blueprint. How do we come up with a clever, elegant solution that transforms this delicate device into a tough, useful new tool?
You know, what's really fascinating here is that we're talking about a complete 180 in design philosophy. A galvanometer has low resistance on purpose so that current can flow through it easily. But a voltmeter, it has to do the exact opposite. To measure voltage correctly, it needs to be like an invisible ghost in the circuit. And to do that, it needs ridiculously high resistance. It needs to be a roadblock so that almost no current from the main circuit gets diverted through it.
And there it is. That's the whole trick. The solution is just so simple, but so effective. We're not rebuilding the whole thing from scratch. We're just adding one key component, a really high resistor wired up right in series with it.
So, how much resistance are we talking about? Is it just a guess? Nope. Physics gives us the exact recipe. This formula right here, this is our blueprint. It tells us precisely the value of the resistor we need to make this hardware mod work perfectly.
Let's just quickly break this down so it's super clear. R is our goal, the thing we're solving for. V is our target, what's the max voltage we want our new voltmeter to handle. IG is a really key spec. It's the tiny amount of current that makes the galvanometer's needle go all the way to the end of the scale. And G is just the galvanometer's own built-in resistance. You plug in those numbers and you get the perfect resistor value.
Okay, the blueprints are done, we've run the numbers, it's time to stop talking and start building. Let's execute this upgrade.
Actually doing it is a simple three-step process. First, you run the math with our formula to get that magic resistance number. Second, you grab a resistance box, which is basically just a box that lets you dial in a very specific resistance, and you connect it in series with the galvanometer. Finally, you just set the resistance on the box to match the value you calculated. And that's it. Our hardware upgrade is efficiently complete.
So the device is built, but we're not done yet. I mean, what's the point of a measuring tool if you don't know if it's right? Now comes the most important part. We have to build a test bench and verify that our new voltmeter isn't just working, but that it's actually accurate.
This is really the moment of truth. Did our plan actually work? To find out, we're going to put our new creation head-to-head against a trusted, factory-calibrated voltmeter. It's a straight-up comparison to see if our DIY instrument can hold its own.
So here's our test bench. We've got a rheostat, which basically works like a dimmer switch for voltage. We can use it to dial the voltage up and down. Then, we connect both the standard voltmeter and our new one in parallel. That's key, because it means they are both trying to read the exact same voltage at the exact same time. It's the ultimate side-by-side test.
Okay, time to collect some data. We'll adjust the rheostat to different voltage levels. At each level, we write down the reading from the standard, trusty voltmeter, we'll call that V2. Then, right next to it, we write down the reading from our own converted device, that's V1. And that final column, that's the one we really care about, the difference, or the error, between the two.
And that final column tells us everything we need to know. If the difference between our reading, V1, and the standard reading, V2, is basically zero across a bunch of different tests, well, then we nailed it. That means our math was right, our build was solid, and our upgrade is a complete success.
So we've built it, we've tested it, we've confirmed it works, but let's just close the loop here and go back to the fundamental question. Why does adding one little resistor have such a huge impact? What's the core principle at play?
This is the secret sauce right here. By adding that massive resistor, we turned our device into a kind of electrical dam. When we connect it to a circuit, its huge resistance means that only the tiniest, most insignificant trickle of current can get through. It lets our device see the electrical pressure, the voltage, without actually stealing any significant current and changing what's happening in the main circuit. And that is the absolute sign of a great voltmeter. Measure, but don't interfere.
And that leaves us with a fun little thought to chew on. We just saw how adding a high resistance in series lets us measure high voltage. But what if you wanted to do the opposite? What if you wanted to upgrade that same galvanometer to measure high current? Well, that's a whole different problem. And it requires an equally clever but totally opposite kind of solution. Something to think about.